All right, and I'll hand things over to group 448L to present Heliotide.
Thank you everyone for coming to our presentation. This is group 448L Heliotide. Our group members consist of Alexander Hong,
Antarinos,
Matthew Patrick,
Marcos Tejada,
Tyler Grenay,
Uchechukwu Ilodibe,
and Zarik George.
Next slide. Okay. We will be presenting our product Heliotide by going over some of the design revisions, iterations, as well as changes we made prototyping the product throughout the semester. In addition, we will also be discussing about some of the testing that we've done as a group in order to ensure our product will meet the customer needs, as well as the total cost of designing the Heliostat and future expansion prototyping ideas for future semester students. Next slide. So a little bit background here for those that don't know, Heliostat is basically a little mirror that reflects concentrated sunlight toward a water drum sitting on top of the tower. And the concentrated sunlight pours the water inside the drum, turning the water into steam. The steam is then fed into a turbine. The turbine drives a generator, which generates electricity. It is similar to a nuclear power plant generation, but rather than using nuclear fission, we're dealing with solar energy, using solar energy from the sun instead. So back to our design, our central design priority is really boiling down to one thing. That is to minimize both the off-the-shelf and 3D printed parts used in order to build a Heliostat. Because of this, we were able to develop a Heliostat that is compact in size, easy to assemble, and most importantly, cost efficient, meeting the tight budget requirement defined by our customers. And as you see, here's a picture of the prototype at the bottom of your screen. Next slide. So to do all of that, we have to go back to the beginning of the semester. We spent a lot of time doing R&D at the beginning. We, as a team, met to discuss all Heliostat designs from previous fall and summer 2021 semesters. For this class, our goal is to prototyping and validating the concept experimentally. So to do that, we started by applying down selection and quantified matrices to all of the designs. Our team was able to eliminate or down select to one ultimate design, like the one you saw in the picture on the last slide. We did some modification and concept generation to the design, mainly on the mirror and the supporting mechanism. But after that, our team started prototyping by 3D printing parts and putting them all together to get what we see here assembled in a cluster configuration.
So as Alex mentioned on that previous slide, our starting point was to evaluate all pre-existing designs from previous semesters with the intention of finding the best design that met the customer needs. So all those pre-existing designs were already a fully fleshed out conceptual design, and our priority this semester was to prototype and validate. So specifically doing that over the course of the semester. And so each of us went through all the pre-existing designs individually, and we selected 4 based on feasibility and how well they met the customer requirements. And so after we individually selected our 4, we reconvened, we shared our selections, and then we selected the 4 most common designs among our selections to put through a house of quality assessment. And so we did a similar approach for some of the customer needs that we wanted to prioritize for this semester. We also put those in the house of quality, and that helped us narrow down our 4 designs that we had selected down to 1 design, which is the winner of the house of quality. So the winner that ended up coming out of that house of quality was fall 2021's group 4 design that you guys see here. And a couple features of it a couple things that distinguish it from other designs were the 3D printed parts that it already had incorporated into its design, the fact that it already had NEMA 17 stepper motors as well incorporated into the design, and it was already a small scale compact design, which all of this went nicely with some of the constraints that we had in class, which were a 4-month timeline. We had to finish it within a semester. The fact that we were highly encouraged to 3D print to rapid prototype, and the fact that we were going to be given specifically NEMA 17 stepper motors to actuate motion. So it ended up going nicely with some of those constraints as well. Yeah. And so here's our final product. This is the Heliotide. So as you can see on the right, these are a couple dimensions, the length, width, and height of the Heliotide. And on the left side here are a couple specs that I'll walk you guys through. So one of the customer requirements was a margin of error of 0.5 degrees. And so essentially the Heliotide is able to redirect sunlight to a specified location with a margin of error of 0.5 degrees, satisfying that customer need. Additionally, our Heliotide also has a 306-degree azimuth range of motion, which is represented by the alpha symbol there, and also a 166-degree range of motion for the elevation, represented by beta, as you can see on the screen. And just to further clarify, just to give a little more information on that 166, it can rotate counterclockwise and clockwise from that orientation you see there on the screen, 83 degrees. So the 83 and the clockwise and counterclockwise adds up to 166. So yeah, just wanted to give a little information there. Additionally, the Heliotide costs $21.33 the prototype. This is excluding the NEMA 17 stepper motors and the electronics that we were provided in class, but we'll get into that a little bit later in the presentation. It has a modular surface area of 75.2 centimeters squared, a factor of safety greater than 2, and it can operate in temperatures between 14 degrees Fahrenheit and 122 degrees Fahrenheit. And so here's just a general overview of some of that R&D that Alex was talking about before that we did this semester, some of the modifications that we made to the pre-existing design. And so the first one being the mirror holder. So we changed the geometry of the mirror holder to better support the mirror itself. The limit switches, we added those to allow the Heliotide to establish a proper homing position. The enclosure was also extended, as you can see there on the right, to allow for electronic components to fit within. And the gear ratio was changed from a 4:1 to a 5:1.
As Marcos just said, one of the design changes we implemented was increasing the gear ratio from a 4:1 to a 5:1. With a stepper motor resolution of 1.8 degrees per step and a customer need of a maximum error of 0.5 degree, the minimum gear ratio to satisfy that requirement would be a 3.6 to 1. And with a 4:1 being so close, we wanted to increase that gear ratio. So increasing it to a 5:1 gave us overall resolution of 0.36 degrees. The parts were designed to be 3D printed, and with that comes a size limit to how small the teeth could be printed with accuracy. So there was a size consideration to how far we could increase the gear ratio as the gears got bigger and bigger. But we determined that a 5:1 gear ratio was enough to satisfy all of the customer requirements that had been laid out. Next slide. With the increase in the gear ratio, that also increases the holding torque, the output holding torque of our Heliostat. So multiplying the motor's holding torque by the gear ratio, we get an output torque of 2.95 Newton meters. And using the same thin airfoil approach with an angle of 10 degrees, we get a new maximum operating wind speed of 11.55 meters per second, or 25.8 miles per hour. This is not the maximum wind speed that the Heliostat can withstand structurally. This is rather the maximum wind speed that the motors can hold their position in, assuming a 0.5 meter by 0.5 meter mirror before the wind overturns the motors. Next slide. Another design change we made, as Marco said, was the mirror holder. The original mirror holder was designed to hold a 0.5 meter by 0.5 meter mirror in high winds. And we just thought that that was unnecessarily excessive for our testing purposes of a 6 inch by 6 inch mirror. So we redesigned the mirror holder and optimized it for 3D printing. And the result is what you see here on the right. While installing the mirror, we found that if the holes in the mirror and the holes in the mirror holder were not aligned properly, the mirror either wouldn't fit or it would buckle under compression. So we made the holes in the mirror holder a little bit larger to give us some wiggle room so that we could ensure that the mirror was in tension during installation and ensure a flat reflective surface.
Continuing on design changes, the motor enclosure was also modified. The original design for the motor enclosure was for it to be 3D printed and use a snap-on concept for mounting. For the prototype, the motor enclosure mounting was changed to screws to secure it better for the wind test. More internal space was added to accommodate motor wires and for future additions like printed circuit boards, if future semester students would like to add those inside of the enclosure. Holes were added for limit switch mounting and sharp corners were replaced with chamfers so that no support material had to be used during 3D printing. Next slide. 3 limit switches were implemented into the Heliostat for purposes of zeroing and safety. 2 were installed in the elevation axis and 1 in the azimuth axis. There are 2 elevation axis switches to stop the movement of the mirror in both directions. If something were to go wrong with the controller and it were to go in one direction or the other one, there's a limit switch there to stop it so that nothing gets damaged. The azimuth axis takes advantage of a peg in the base gear to actuate it, making it so that the limit switch does not limit the movement of the Heliostat. Next slide. For aiming of the Heliostat after zeroing in the azimuth and elevation axes, equations were developed that could be simultaneously solved to find both angles when given x, y, and z coordinates. This was done by correcting the given coordinates with the current position of the center of the mirror. As the position of the center of the mirror is a function of the angles, the equations must be simultaneously solved to get the correct values. These angles give the initial positioning of the mirror so that the final movements can be done for calibration.
In order to validate our prototype in a laboratory environment and achieve technology readiness level 4, it was subjected to a battery of tests to collect evidence that the performance requirements set forth by the customer might be attainable. The first defining test was a wind survivability test to demonstrate that our prototype, which is aerodynamically similar to our final design, can withstand the most extreme weather conditions possible at the target installation site in Las Vegas, Nevada, with a factor of safety greater than 2. Whilst in its normal operation mode, the prototype was subjected to wind speeds of 9 to 12 miles per hour, and whilst in its safety mode, it was subjected to higher wind speeds of 90 to 134 miles per hour. For both speeds, the prototype was rotating at a rate of 3 revolutions per minute to simulate varying wind conditions, as shown in the videos in the background. And I'm happy to report that our prototype was able to successfully complete both of those tests. Next slide, please. The second defining test was a laser reflection test to demonstrate that our prototype can reflect light from a vertical laser source to a distant target with a 0.5 degree conical angle to meet the customer requirements. The test consisted of 5 unique targets with escalating levels of difficulty, ranging from human commanded closed loop control of a known target to open loop control of an unknown target. Our prototype was able to accurately reflect light to all targets as specified, as you can see in the videos as a background, as you can see in the videos in the background as well.
So to provide an overview of some design highlights, we believe these key features help our prototype stand out from the rest. To start, our design's small compact size allows for easy scalability and arrangement in the Heliostat field. Along with this, the Heliotide's low part count, coming in at a total of 57 parts, including fasteners, provides for ease of manufacturability, assembly, and repair. The last feature, our design's frame adaptability for square geometries, allows for variability in mounting, base modifications, and implementation. Next slide. To gain a better understanding of the assembly and the parts that our Heliostat design incorporates, here are some exploded views of key sections of our prototype, along with a video of the exploded CAD model. In the animation on the right side of the slide, you can see each of these key sections being exploded, showing their specific components and how they are incorporated into our design. Next slide. To portray our Heliostat's prototype cost summary, here's a table of the base cost and unique cost. The base cost table represents products and components provided to us through the course that were outside of our $100 budget and purchase orders. The unique cost table represents the products that our group ordered in addition to the provided products. The total cost to build our prototype design was $162.80. This slide shows the base and unique cost tables for the scenario of building 3,000 modules of our prototype for a Heliostat field. To adapt to the large production, the unique cost substitutes 3D printing for plastic injection molding. The cost per Heliostat in this case would come in at $150.60. The total cost to produce the total 3,000 modules was calculated to be $406,620. This cost was computed by multiplying the cost per Heliostat for injection molding by the number of units and applying a 10% discount to account for bulk purchase order discounts.
As this is a prototype, certain changes would have to be made to accommodate for the final version to be used in the field. Firstly, we could 3D print most of our parts for rapid prototyping, but that sacrifices strength, and it can be very tricky to perform a strength analysis on a 3D printed part. So we'll need to use stronger materials like metals to manufacture some parts. Next, since we need to prevent dust, craters, and rain from affecting our heliostat, we need to enclose the gears with materials like bellows to protect the parts from atmospheric conditions. Also, we can reduce the backlash in the gears by slightly reducing the spacing between the gears. This will help reduce the amount of lost motion in the system. Next slide. The Heliostat support system uses a square tubing and will be adaptable to other Heliostat frames. So if, for instance, our design isn't chosen and a different frame geometry is chosen to build the final Heliostat, our support structure can easily hold the frame up and can also be anchored to the floor. Next slide. So why Heliotide? Why choose our design? As mentioned earlier, the Heliotide has a small number of OTS parts, that's easy to manufacture and assemble, and has a solid foundation for future adaptability. And as a bonus, it passed all the design tests conducted for this class. Next slide. To wrap things up, we'd like to thank all our corporate sponsors, Cummins, Northrop Grumman, Carrier, Origo, and every other sponsor, professor, or teaching assistant that helped us in this journey. If anyone has any questions, please feel free to ask.
All right, great. Thanks for the presentation. Do we have any questions from our panelists?
So I don't have questions, but I do have a couple of comments. I thought, this is Rick Miles, Northrop Grumman. I really appreciate it, again, that you did a good job explaining what the specific task was for the semester and how that worked in the overall development of the project scope, right, for going through these classes. Also thought you did a nice job of making sure to talk about subbing out 3D printing with plastic injection molding in your cost, and addressing the production cost reduction that you would get going to a mass production. One of the things, if you could go back to your cost slide.
Mhm.
Okay, sorry, I must have just looked away for a while. I had missed that you reduced the price on the 3,000 units, so all good. Okay, that's it.
Okay, any other questions? Oh, I see Dr. Dong unmuting herself.
Yeah, so one question is on the slide, new maximum operating wind speed. I don't know the page number, but could you please change to that slide?
Was it this slide here? With
It's in the design changes right after the gear ratio.
Okay. Oh, I got you.
Yeah, so the first tau not equal to GR times tau M. What does that mean?
That was the holding torque of the motors multiplied by the gear ratio.
Why you use tau as a torque?
I've used that in other classes before.
Okay. Maybe I'm wrong, but normally, well, from the I taught mechanics materials, aerospace structure, and FEA. We normally use capital T as torque and tau as shear stress. And when I read this slide, I feel all of the confusion because, well, your unit is Newton meter and you use the tau, but maybe it's fine. It's probably just my habit. I use the capital T.
All right, sorry for that confusion. Yeah, that is, we can look into that and fix it for our FDR if that is an incorrect symbol. But
Yeah, so could you please refer to which textbook you use tau as the torque? I can check the textbook.
I can't recall.
Okay, sure.
Yeah.
Sure, that's fine. It's just small things. And another thing that I think one student mentioned that to prevent have the buckling during the installation, so you put some tension. There is some tension when you install the mirror. Yes, I definitely agree that we need to avoid the buckling when we install. But do you consider that the pre-existing tension will also cause some problem when you install the mirror?
So the thing with the mirror, if we can go to the mirror holder picture. So when we originally printed it, we kind of did a very light clearance fit. The bolts on the right go through that mirror holder, which is the white plastic pieces that is holding up the mirror. And if you have a very tight tolerance on that bolt for that hole, if you don't have an exact fit for all 4 holes, something's gonna have to bend in the mirror or the mirror holder to make sure you can attach it. So what we did for the second iteration of the mirror holder was make the bolt holes bigger so that we don't have to worry about that tolerancing, because we had to kind of hand drill the holes into the mirror. And you can't guarantee that you're gonna get a really good placement of that drilled hole. So bolt holes bigger so that when we put the mirror on, we're able to lay the mirror on flat onto the mirror holder, put the bolt holes where it is at that moment without having to worry about fitting it through 2 different holes, basically. So that's kind of the idea of why we made the hole holes bigger, to ensure that we have that flatness of the mirror when we install it, and then tighten the nuts on it.
How do you know it is tension?
So I feel tension might be a bad word to use, because
I was going to clarify, it's not in high tension. It's just with a little bit of wiggle room, we were able to kind of pull the bolts apart enough that it would eliminate any sort of buckling and allow for the flatness. Because with proper tools and better manufacturing, you could probably drill exact holes into the acrylic mirror. But with the drills that we had, and the possibility of cracking it, we kind of just came up with a quick solution for the prototype to just make sure that we could pull it tight and flat.
Okay. Because when I heard you guys talk about in the presentation, you say, okay, we install by drilling a hole, and then when we install, did that tension there. And what I feel like is, okay, when you drill a hole, it's not like perfect drilling, no micro crack around, and now you have tension, you have stress concentration around the hole, and you have micro crack when you're drilling the hole. That can cause potential risk. So yeah, I appreciate your back explanation. That's all my question. Thank you.
Thank you.
All right. Any more questions from the panel? Okay. Well, seeing no questions, we think we can safely wrap it up there. So I just want to thank you guys for sharing your presentation with us this afternoon, and all of the hard work that you guys put in this whole semester to get this thing from an idea on a piece of paper to a functioning heliostat that's able to hit targets and carry out the the principal goal of the semester, which is to figure out how the mechanism is going to work for us to get the sun into onto the concentration tower. So I really appreciate you guys spending all semester working really hard on this thing. You made you guys make me look very good, right? Like, you guys did all the hard work, and a lot of the faculty are sending in a lot of emails about how impressive every group is this semester. So appreciate that from you guys. Thank you so much.
Thank you.
Thank you for
for
coming.
leading the class. Yeah.
Very good. Okay, so with that, let me stop recording.